Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year was 1834. Carl Gustav Jacob Jacobi, a name synonymous with profound contributions to mathematics, penned a pivotal paper titled On the Formation and Properties of Determinants. This work, far from a mere exposition, represents a cornerstone in the development of linear algebra, a domain that continues to shape advancements across countless scientific and engineering disciplines. To fully appreciate Jacobis' achievement, one must first understand the intellectual landscape he navigated, the prevailing mathematical currents that informed his approach, and the specific challenges he set out to. Prior to Jacobis' seminal work, the concept of determinants, though known and utilized, resided in a state of relative immaturity. Mathematicians such as Leibniz and Kramer had touched upon the subject, primarily in the context of solving systems of linear equations. However, the treatment lacked a unified framework, a general theory that encapsulated the essence of these objects and systematized their properties. The focus remained largely on computational techniques, centered on formulas for calculating determinants through specific methods, particularly for small orders. The lack of a robust theoretical foundation hindered a deeper understanding of their nature and their potential applications. This was a terrain that Jacobi surveyed, the existing knowledge fragmented and awaiting a unifying vision. Jacobi perceived the need for a systematic treatment, one that elucidated the intrinsic properties of determinants and provided a foundation for their more widespread application. Jacobis' groundbreaking contribution resided in his methodical and comprehensive exploration of determinants. His paper did far more than reiterate known formulas. It established a coherent theory, a carefully constructed edifice built upon rigorous foundations. He provided a precise definition of determinants, expressed in terms of permutations, and then proceeded to explore their properties with a clarity and elegance previously unseen. His work offered a novel perspective, one that transformed determinants from mere computational tools into fundamental objects of mathematical study. The work delved deep into the properties of determinants. Jacobi explored how they behaved under various transformations, such as row and column operations. He rigorously established theorems concerning the determinant of a product of matrices, a vital result that would prove indispensable in later developments. He further investigated the concept of minors and cofactors, revealing their intricate relationships with the overall determinant value. Jacobi also addressed practical aspects of determinant calculation, developing efficient methods for evaluating determinants of various special forms. He offered innovative techniques that significantly streamlined the computational process, reducing the complexity of solving linear systems, particularly those with a large number of variables. The immediate impact of Jacobis' work was considerable. It provided a systematic methodology for solving systems of linear equations, a problem encountered across various scientific disciplines and engineering applications. It furnished the tools necessary for analyzing the properties of linear transformations, thereby facilitating a more profound comprehension of linear spaces and their characteristics. The study of determinants then became linked with the study of matrices. Matrices became a vital tool for organizing the coefficients in the set of equations, and the determinant could provide insight into various properties of the system itself. This laid the groundwork for a more formalized treatment of linear algebra in the ensuing decades. Jacobis' contributions resonated far beyond the immediate context of linear algebra. His work influenced areas from differential equations to number theory. For instance, his techniques for handling determinants found applications in the study of linear differential equations, offering new strategies for solving and analyzing these equations. Moreover, Jacobis' work in number theory, especially his investigations of elliptic functions, were deeply interwoven with his understanding of determinants and matrices, highlighting the interconnectedness of mathematical domains. His work provided critical tools for the study of multiple integrals, facilitating the transformation of variables in multidimensional spaces. The Jacobian determinant, a direct consequence of his theory, became an indispensable concept in multivariable calculus, enabling the accurate computation of volume integrals in complex domains. Subsequent mathematicians built upon Jacobis' foundational work, expanding and refining the theory of determinants and matrices. The concept of matrix eigenvalues and eigenvectors emerged, enabling a deeper understanding of linear transformations and their relationship to determinants. Arthur Cayley, a prominent figure in the 19th century, further developed the theory of matrices, formalizing their algebraic properties and establishing the concept of matrix operations. James Joseph Sylvester contributed significantly to the theory of invariance and covariance, concepts that were intrinsically linked to matrix theory and determinant theory. William Rowan Hamilton introduced quaternions, an extension of complex numbers, the study of which further stimulated the investigation of matrices and linear algebra. These mathematicians, among many others, relied on Jacobus' framework, demonstrating the enduring influence of his. The reception of Jacobus' work was generally positive, although the inherent complexity of the subject initially proved challenging for some. The systematic and rigorous nature of his approach garnered immediate respect from his peers. The methods he developed were widely adopted. It was, arguably, a work whose intrinsic merit and profound implications were soon recognized. The concept of a determinant has a somewhat counter-intuitive nature, a notion that initially sent shivers down the spines of even the most seasoned mathematicians. The utility of his methods facilitated concrete progress and offered a more unified understanding of linear systems. Jacobus' intellectual trajectory was influenced by several preceding mathematicians and existing problems. His work drew upon the contributions of mathematicians from a variety of backgrounds who grappled with systems of linear equations. The methods of Lagrange on the subject of elimination in algebraic equations were important. The work of Cauchy, who had already begun investigating determinants, also helped develop Jacobus' insights. Furthermore, the need to solve complex systems of equations that arose in areas such as physics and astronomy compelled mathematically inclined minds to engage with the subject. Jacobi was certainly aware of these works when he began structuring his ideas. He synthesized multiple contributions into a framework. The legacy of Jacobus' work is profound and far-reaching. His rigorous development of determinant theory established the foundations for linear algebra. The properties and results that he described are still foundational in the study of the subject today. His work on determinants has made its way into various fields, and its influence on the contemporary sciences is undeniable. The Jacobian determinant, which he introduced as a pivotal tool for handling transformations of variables in multiple integrals, remains an indispensable tool in modern calculus and its applications. Jacobus' influence can be traced across physics, engineering, computer science, and statistics. In short, Jacobus' 1834 paper on determinants established him as a pivotal figure in mathematics, forever altering the landscape of algebra and its myriad applications. His work continues to resonate, serving as a testament to the power of rigorous thought and the enduring impact of foundational mathematical contributions. His work endures as a standard for mathematical rigor and clarity, a constant reminder of the profound impact of systematization and the power of a well-defined theory.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.